Weight, people use this interchangeably with mass sometimes, but it really isn't. Weight is really a force. Mass is a quantity of matter. Weight is a force. Force applied to an object, but that force is applied because of gravity. Well, Newton's second law still applies when gravity is the acceleration. So the force due to weight is m times g. The general equation, remember Newton's second law, is F equals ma. But if your acceleration is the gravity acceleration, well then it's mg, and that means it's a weight. So this is another useful tool, another version of Newton's second law that applies to the special case of weight. Let's take a look at this problem. The question is, how much does a 400 kilogram bag of popcorn weigh? Some people might say, well, it weighs 400 kilograms, but 400 kilograms really isn't a weight. 400 kilograms is mass. The force that we call weight is equal to mass times g, the acceleration due to gravity. So to find this out, we'll just plug in these numbers. Mass is 400 kilograms, and we're multiplying that by g. Well, g is 9.80 meters per square second. That's the acceleration due to gravity. No units cancel, so we end up with the compound unit of kilogram meters per second squared. But recall, kilogram meters per second squared is newtons. Let's find out what the number actually is. Pull our calculator back in place here. And we'll do the arithmetic. 400 times 9.8, and it returns to us 3920. So we would say 3,920 newtons is how much the popcorn weighs. Well, Newton's third law of motion is kind of obvious, and people know this from a very early age because it's taught in schools, but not a lot of people have a good feel for what it means, and it sometimes screws people up when they solve problems. It simply states this: for every force that acts on an object, the object exerts a force, and that force is equal in magnitude, so it's going to be the same size. If I push on you, you're going to push back on me with the same force, and it's opposite in direction. So if I push you east, you're going to push back west. Here's an illustration of Newton's third law of motion. Kid is pulling a wagon down the road. The wagon is actually moving, so there's an unbalanced force on the wagon itself. But at the intersection of wagon and child, we have two forces that are equal and opposite. This wagon pulls back on the kid just as hard as the kid pulls on the wagon. Those forces are matched. For every force in the universe, there's an equal and opposite force. Sometimes it's not obvious to us what that force is. Sometimes we have to look for it. Well, here's an example problem for you to try. What's the force acting on the ground when a 100 kilogram man stands on the ground? Stop the video and try and solve this. Remember, you're looking for a force. 100 kilograms is a mass. Okay, here's how you'd solve this. We're looking for force, so F is the unknown here. This is a mass. Here's a picture of our guy. He's standing there on the ground, and he exerts a force. We call that force weight. And force due to weight is mass times acceleration, like all forces, but the acceleration in this case is gravity. So we plug in our numbers here. The guy's mass is 100 kilograms. G, everywhere on Earth, is 9.80 meters per square second. So when we multiply out here, we're going to get 980 kilogram meters per square second, or 980 newtons. That's the force the guy exerts on the ground. Try this one. This throws a little wrinkle into things. The person isn't just standing on the ground, but this person jumps down from 2 meters high and compresses the mud 2 centimeters as he comes to a stop. That's actually going to put more force on the ground than if he were just standing there. Why don't you give this one a try? This is asking, what's the force acting on the ground when a 100 kilogram man jumps to the ground from 2 meters high? Now that's different than just standing there. Those of you who run know that you buy cushiony running shoes because landing from up above the ground puts more force on you, and on the ground therefore, than just standing there. And so you buy these compressible cushiony shoes. So he compresses the mud by 2 centimeters as he stops. Think about that and try and figure out what the force acting on the ground and therefore on the person would be when this guy jumps down. Stop the video and give it a try.
Okay, let's start out this problem by modeling, by drawing a picture. Here's our little cliff that the guy's jumping off of. We know that this is 2 meters down. We know something about our guy. We know that his mass equals 100 kilograms. That's the mass that he has. So he's going to jump. He's going to jump down here, and he'll reach some speed by the time he hits the mud. But the mud here is 2 centimeters thick, and that's what's going to stop him. Now, if you do the math in your head, 2 centimeters is 0.02 in meters, and that's probably what we're going to want as we go through our calculations. Well, here's what we're shooting for. F equals ma. That's what we got to find. This we know, 100 kilograms. That, not so much. So what we're going to have to figure out is how much does he get accelerated by the mud. Some people would say decelerated, but his speed slows down because a force causes him to accelerate upwards. Well, to know how much he gets accelerated here, we're probably going to have to know how fast he's going when he hits the mud. We know when he finally gets to the bottom of the mud, his speed down here will be equal to 0. So if we can find out what his speed is at the top of the mud, well, we'll be well on our way. I think we can do that from the free fall stuff that we learned in the last section. We know that this guy is acted on by gravity, and so his acceleration downward from the top of the cliff is g, 9.80 meters per second. Up here, we're going to assume, before he jumps down, that his velocity is nothing. So we'll figure that out using this equation. We know that final velocity is equal to the square root of the initial velocity squared plus 2 times a times d in general. But for this guy, in this situation, his initial velocity at the top of the cliff is 0, and a we know to be g. So we could say the final velocity at the end of the fall is equal to the square root of 2 times g times d. Let's put some numbers to that. Square root of 2 times 9.80 meters per square second times 2 meters, which is how far he falls. Let's grab a calculator and do these calculations. 2 times 9.8 times 2, 39.2. We'll take the square root of that. Well, here's what we get. At the end of his fall, in other words, at the top of the mud, he's doing 6.26, and the units are meters squared per second squared, square rooted, which is just meters per second. Okay, now that we know he's going, not question mark anymore, but 6.26 meters per second, how can we figure out the acceleration that's going on here? Well, looking at this equation again, if you know a final velocity, which we do, it's 0, a starting velocity, which we do, 6.26, and you know a distance, which we do, 0.02 meters, you can figure out acceleration. That's the only unknown in this equation. So let's solve that equation for acceleration. Starting out this way, Vf equals Vi squared plus 2 times A times D under the radical. Well, I think I'm going to make my life easy because I know that V is 0 when he's done. So that's Vf is 0. I'm going to plug that in before I do any more algebra. 0 is equal to the square root of Vi squared plus 2 times A times D. Now if I square both sides, well, that's pretty nice because 0 squared is still 0. So 0 is Vi squared plus 2 times A times D. Slide down a bit. Now, I want to solve for A, so I'm going to subtract 2AD from both sides. Leaves me with this, minus 2AD is equal to VI squared. Well, if I divide both sides by 2D, negative 2D in fact, here's what I get. Acceleration, which is what I'm trying to find, is equal to VI squared divided by -2 times d. Well, VI was our 6.26 meters per second. So let's plug the numbers in. 6.26 meters per second, and that quantity is going to be squared, divided by -2 times the d. Well, the distance was 0.02 meters because it was 2 centimeters. Well, let's look what happens to the units. Meters drop out of here, but meters per second are squared in the top, so you're only dropping out 1 meter. 1 is still left. No seconds cancel, so it's going to be meters per square second. That's good, because those are units of A. Well, now let's do our calculations. 6.26 squared divided by -2 times 0.02. Here's what we get. Minus, I'm going to round to 980. Minus 980 meters per square second is the acceleration. Okay, here's what the negative sign means. His velocity was down. He stops, so his A must have been up the opposite direction, so the opposite algebraic sign. Okay, the only point of finding A here was so we could put it back in this equation, because ultimately what we needed was force. Force is equal to mass times acceleration, and we remember that this guy's mass was 100 kilograms, so when we multiply that by the 980 meters per square second, I'm leaving off the negative sign now that I remember what that means, I just multiplied these two things together. So it's 980, 2 more zeros. Okay, the force on this guy is 98,000 kilogram meters per square second, or 98,000 newtons. It's a big number. Well, there's a lot of force when you stop from a fall.